Yes, Thomas is here. Cool. It's my great pleasure to welcome Thomas House, who is at Manchester University and also one of the co-investigators on the Juniper Consortium. He's going to be talking about some work looking at the role of school children in bringing infection back into the households. So with that, I'll pass over to you, Thomas.
Hello, so thanks for the invite. So despite our no pandemic response being perfect, the UK government has done some really excellent pandemic science, and that's included two very large surveillance studies. So REACT has this individual-based cross-sectional design. So that means they have a wave, and in the wave, they sample a lot of people. The Office for National Statistics study has a household-based longitudinal design. So these are complementary, but the household-based one is more complex, right? That's what I'm going to talk about. Of course, we've also got case finding, death and hospitalization data, the COVID symptom study of Zoe and so on. But as we're seeing, a lot of the pandemic response is being wound down. So the ONS study is going to have this kind of increasing relative importance to thinking about some of these questions. Just so people know anything, there's an awful lot of stuff on this website that you can get if you'd like it. So getting the raw data, well, no one sees the raw data. Working with even the anonymized data requires being in a trusted research environment. But an awful lot of the outputs are available for free, completely freely. You can download CSV files and so on at this site. One of the reasons that you want to study households is people live in households, but the other thing is that each household is like a little repeatable experiment about infection. And the point is that unlike an experiment where people used to do ones where they deliberately infect mice or something, right, which is quite horrible, but you, unlike that, it's ethical because it would have happened anyway, right? So you're observing a natural process. And so each household is like a little repeatable experiment of transmission that we can learn about transmission from. Now the issue, well, not the issue, but case finding tends to be faster, okay? Because case finding, like in test and trace, is a measure of incidence. So in the past, the ONS studies tended to play this more confirmatory role, or say that it doesn't suffer from the sampling biases of test and trace. And actually those sampling biases can be quite considerable, as we've seen. So this wasn't a trivial thing, but even getting a crude estimate, generally speaking, test and trace wouldn't be it would be in the right ballpark. But as test and trace capacity is wound down, it's going to be more important to look at these data for the kind of first attempt at an estimate. Okay, so just so people know, if so apologies to people who've seen these slides before. I'm giving the same talk pretty much throughout the pandemic and calling it different things. So make yourself a cup of tea or something if you've seen this. But the close repeated nature of these kind of contact means that there is a reasonable amount of transmission, although it's far from 100% as people often think it is. Sorry, I've jumped. Right. Most people do live in households, and a lot of interventions are household level interventions, right? So, like I said, the history of this goes right back to the 1918 flu. Reed and Frost's unpublished work, allegedly simulated in Monte Carlo using a modified roulette table. Bailey developed a lot of interesting theory for mathematicians. His work on epidemics is often kind of seen as being related to what's called spectral methods in applied probability, which we now kind of teach to undergraduates. But I think he was one of the first people to develop these as a way of getting explicit solutions for stochastic models. Then in the late 20th century, we get the general final size formula by Frank Ball. Lots of nice statistical work from Cheryl Addy, Ira Longini, Betts Halloran, people like that. There was the big Tecumseh study on flu. And now we have even better computers, but I'm going to use the Ball equations, right? But we have better data, much better data collection than they had in Tecumseh, because we can do PCR and these other things. Right? So this is a schematic of the ONS design. You have repeated visits, and in each visit you test everyone in the household. Okay, so there's less sampling bias, but it's less timely, because this could be in an idealized test and trace, you catch each person pretty much at the event, as the event happens, and you know who was first, and you see it at the time the infection starts, not just at a point in time. So, you know, in this design, you can quite late in the infection. So that's what I mean about test and trace gets in first. And they're also able to do this more straightforward analysis where they say, well, the person who we found first is the index case, and other people are secondary cases, and then they regress secondary, then they regress probability of being a secondary case on properties of the primary and secondary case, and they can just do kind of logistic regression or something, other kinds of regression on that. That's not possible in this case. A lot of people are saying, well, how do you identify the primary case? And the answer is we don't. I use the Ball equations to integrate over the different possibilities, right? So just going to say a quick thing about these secondary attack rates, crude secondary attack rates. You can also calculate those in this. So here, the crude secondary attack rate would be a half, right? Because there was at least one case, and then of the 3 people who could have been secondary cases, sorry, I'm getting it wrong. It's 2/3, sorry, here is the secondary attack rate in this picture, right? There's one primary case. We don't know which one it is, but that doesn't matter, right? Then there are 3 people who could have been secondary cases, and of those 3, 2 are secondary cases, right? We don't need to identify them as individual primary and secondary cases to say here, the secondary attack rate is 2/3, right? And that's what this equation 1 here says, that you can just take out one person in the household and work out a crude secondary attack rate, and then compare that to studies with the tracing design. Okay, so that's what we did here. Oh, sorry, these are too small. But basically what this is doing is we stratified the household into whole groups of household, depending on whether they were vaccinated, had significant vaccination in the household or not. I.e. that we meant significance in at least one person who was at least 3 weeks after a full course of vaccines, right? Then there was people who weren't at all vaccinated. Then there was a group in between where some people were partially vaccinated or whatever, you know. And what you see is that the secondary attack rates are further right in the people who are not vaccinated, right? So this is good. The vaccine stops onward transmission. It's not, you know, it's a significant reduction to transmission. Clearly, it's not sterilizing about secondary transmission in the same way that, you know, if you have a measles jab, you just don't get it, but it has a significant improvement on within household transmission risks, aggregate transmission risks. But what we see is that significant improvement is reduced as we move through to Omicron to things that are more like vaccine escapes. That's what the bottom line says. So this is the kind of insight you can get from this sort of data. And there's some tables of that. So this is just being written up. But on to the main topic of today. Here's why the household is important, right? That in a lot of people's minds, you have a kind of chain, you know, the household is a link in a chain, right? So each household will have some people attending a workplace and some people attending a school. Well, not every household, right? But a lot of households have some people in workplaces and some in schools. So you could have, you know, key workers in the bottom right in the hospitals where there's always going to be some COVID because the people with COVID go to hospital. They go back into a household, they can infect their children go to school, that school lets it get into another household, which lets it get into another workplace. Maybe this is a key, you know, a power plant or something where people still have to go in and they go to, you know, so the household is, you know, if we did something really horrible and made everyone live at work, right, which you know, some people did do, to break those chains, right, then in a way that would help us segment the epidemic. But in practice, no country's managed really widespread removal of people from the households, right? Not least because a lot of children need care in the household. A lot of people in the household need care from people who need to work. So this is the kind of rough picture. And actually these multi-group models, they're called, are really interesting in their own right. And really, they're kind of mathematically tractable, but maybe slightly under analyzed. There've been some really nice papers on these multi-group ones. So this work is, the main bit of the work is based on this paper in Statistical Methods in Medical Research. I developed the methodology with Timken and Dewey, and I developed the methodology, and it's based on these Ball-Addy type final size equations. And the justification, the reason we call it tranche work, is we split the epidemic into different tranches and used time as what epidemiologists call an instrumental variable, right? So time is used to determine, we'll see different effect sizes at different times, and then we sort of attribute those to policy changes, right? So it's it's all about associations, not causal inference, but if those associations are consistent with known effects of things on each other, then good, right? So this is what I mean by the tranches. So this was like a period of time where there was low prevalence, the school was closed, no variants of concern, no vaccine. Yeah. Then there's a period here where there's high prevalence, alpha was sort of coming but pretty negligible, no Delta variant, no vaccine. Yeah. Then later in 2020 we had high prevalence, schools open, alpha variant was dominant or becoming dominant, no Delta variant, very little vaccine and so on. So each of these time periods is chosen to be big enough to give us statistical power, but kind of small enough that we can see things changing. And at each one, we look at swab positivity, household size, alpha and delta variant, and later at Omicron variants, right? And age of participant, right? So for this workshop, the important one is the effect of age and work in patient-facing roles, okay? And the first thing about the ONS is it is a very, 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 very big data set, right? In infectious terms, it's enormous. We'll never get another study done like that unless there's an equally severe pandemic. So it has, even early on, they were ramping up to 100,000 participants. It ended up at 300,000, and so there's a lot of observations, right? So what's a household? Well, households are, in this case, a unique, all this maths is saying is the households are a unique partition of the sample, right? So each person is in exactly one household, and each household has it contains a finite number of the sample, right? And the households are disjoint, they don't overlap. Okay, so this, and then the size of the eighth household we'll call NA. And that's the size of the set of integers labeling people in the household. Then each person has a feature vector if we're being machine learners, or covariate vector of covariates if we're being statisticians. Xi associated with the ith individual, and we'll let yi be their test result in the tranche, which is 1 if they have a positive swab during that time period, and 0 if not. And we also include people where someone else in their household had one in the time period, but they became infectious later, right? So we associate houses with the tranche where we first observed a positive in that household overall. Okay. So just a quick bit of exploratory analysis. These are histograms by count of people in the household. And the thing to note about these is, so we've taken out the households with no one in because prevalences were pretty small, so that it's dominated by 0. But what you see is these are very, very, very far from binomial, right? So they're over dispersed. There are very many more households that have 2 positives in than you would expect from squaring the probability of having 1, right? And very many more have 3 in than you'd expect from cubing the probability of having 1, yeah? And in some cases, you even see this U shape where the probability of having 5 is bigger than the probability of having 4. And that's a signal of transmission, right? So this goes back to Bull, Mollison and Scalia-Tomba's work in the late 90s, looking at exactly this. Where basically they said, oh, look, you can identify how much is within the household and how much is between, right? Okay, and then the other thing we can do is do that in 2D. Yeah, so we can have some 2D density plots and look at and see. So at each point in the proportion of child positives and the proportion of adult positives, right? We see, we put down a little translucent marker. Yeah, that's what these plots are. They're sort of density plots. And so you see that bimodality even more strongly, right? That it's not a centered distribution. A lot of the weight is on the edges. But what we also see just in the data, this is just a raw data analysis, is there are some households where we only see child positives. And so even before we've done all the formal analysis, this was a bit of a smoking gun for we'd really hoped that children weren't going to play this big role in transmission, and they don't proportional to the number of contacts they have, but they play a non-negligible role in transmission, right? So this is the problem, right, with children in this pandemic, that they're low risk, but their role in transmission can't just be ignored. Okay. So then we did this residual analysis, and residuals let us tabulate features of positives in households in a way that lets us look at how they cluster in the household, right? These are just definitions of Pearson residuals, but this was looking at the clustering of alpha and delta. So basically, just a way of interpreting this is these green squares are ones where you have a positive residual, and what that's telling you is that the gene patterns, whether you're an S positive or S negative, which is indicative of whether you're alpha or delta, certainly when one of those strains is taking over, right? Not when everything's just one strain, right? But when there's some appreciable amount of both strains, okay, that is significantly more correlated in households than you'd expect from the level in the community, and that's again a kind of indicative of transmission, right? So the maths is there for people who are interested in it, but basically what you need to do to get the insight out of the data to do with clustering formally is solve these Ball equations. So because the outcomes are not independent, so whether I get COVID depends on whether someone I share a household with gets COVID, not just on my properties or some random effect of the household, right? So you need this full set of equations for every possible outcome. And what we did is we add covariates to this, right? So this is a model where every individual is differentiated, but there's a rate lambda ij of the ith person infecting the jth person. And if you try and have a parameter for every possible combination of that's too many parameters and you can't identify it from data. So what we do is put effects into covariates, one of which is going to be which school what school year you're in, and learn the effects of those covariates, right? So this is just saying why these equations take this form, and I probably should have taken these slides out for this talk. So that's the technical bit. I guess it's worth saying a little bit. So basically, this Selke construction, it lets you deal with the equations as a non-Markov chain. So I said Bailey came up with these spectral methods. This is in a way the generalization of that to something where it doesn't have to be Markov, right? So we give each individual an arbitrarily distributed stochastic variable for its infectious period, and then each person picks from an exponential one what their sort of resistance to infection is going to be. Then we reduce that resistance deterministically according to the amount of infection about, and the person becomes infectious when their threshold goes below 1. Yeah, and you follow that through, and you get this set of coupled probabilities in 2. The equation looks like this, and the reason the Laplace transform comes in is because of the Selke transformations. You need the Laplace transformation of the distribution of infection times. Okay. And then we put covariates on the risk of infection coming into the household, the transmissibility of each person, and the susceptibility of each person. Yeah, of each type. Okay. Then this was done as a maximum a posteriori, or this was done as Bayesian inference under the Laplace approximation, right? Because the data is so big and the secure environment is not a supercomputer. So there's a closed form likelihood. We add a bit of prior, then make the Laplace approximation and multi-restart numerical approximation. So these, I like to interpret this as a prior it would give the same results as using a ridge and doing a maximum likelihood estimate, right? But I think people tend to interpret the output of these things as Bayesians anyway, so we might as well say it's Bayesian inference. And Laplace approximation. So these are the point estimates, but they're easier to visualize. So this first plot shows the probability of infection during the tranche. So I said like tranche 1 is this low prevalence one, 2, 3, 4 are high prevalence, and 5 and 6 are kind of, you know, lower prevalence again because they were after the lockdown, and while things were being kept low as Delta emerged and we got people vaccinated. Yeah. And then these are the probabilities of transmission within households. They do seem to go up after summer. I suspect that summer is, I personally believe this is evidence that just being in summer reduces transmission, right? Very, very weak evidence, but you know, if people have the windows open more at home or are socializing with their family more outside, all these other things we know are safer, that would make sense for the within household probabilities to be lower. But there are other hypotheses consistent with that. It isn't yet, like I say, this is association, not causation. So that's my hypothesis. Then during this very high prevalence bit of wave 2, the probabilities were all quite high, and then we see them drop. And here I think there's only really one explanation for why they drop, and that's vaccination, right? Because they sort of should have been higher with Delta, right? So it's Delta, but the vaccines are just good enough to make it lower, as well as the Delta increased transmissibility, right? Then these are the effect sizes. So I'll just say something quickly that this transmissibility is related to the pattern of gene positivity. And this model is sort of adjusting for low viral load infections, because something that doesn't have OR plus N or OR plus N plus S, which is the baseline positive, is probably quite viral load. So it could be that if children are less susceptible or transmissible because they are lower viral load, that could be getting absorbed into here, and we'd see less of an effect directly by age, right? So there's just some caution in interpretation. But what we see here is that wild type is less infectious than, so what I'm saying, before the emergence of alpha, being S negative meant you were lower viral load, so less transmissible. Then during alpha, being S negative meant you were more transmissible. Then during delta, it meant you were less transmissible because you were probably an alpha competing against delta, right? Then we don't see very strong effects of transmissibility or susceptibility by age, except when we were not vaccinating kids, right? So what's the difference here with the susceptibility of over 12s in tranche 6? Well, they were the people who, under 12s, they were the people who were not vaccinated. So they were more likely to get infected, right, than other ages. That's the time we see a really clear effect size, right? So this is why I think the vaccines explains a lot of this pink thing here. Then working and patient facing, again, this is why I think the vaccines is relevant, that working patient facing was always more risk of bringing infection in until post-vaccination, right? Then the other thing we see is, though, this is the most important bit for this event, is that when the schools are open, children are more likely to bring it home, which is not the answer we want, because we want the schools open and no COVID, but there was no double win, right? Of just we can open the schools and there's no transmission. There was a trade-off, right? Which was unfortunate and made the policy making hard, but sometimes you just have to say what's true, and then the policymakers have to make that decision. And just to say,
Thomas,
we're continuing. Oh,
Thomas,
yeah,
you've got about a couple of minutes.
I'm done. Yeah.
Okay.
So we're updating this analysis, and here's the latest version. I could talk through all the stuff that's happened in the other tranches, but we do that online in the GitHub. We do this plot a little bit better now as well, dividing the external force of infection by the amount of time that the wave has gone on for. But most importantly, again, this pattern of of the school-age children bringing it in is just there, and is actually, if anything, much stronger during Omicron, because there's been an awful, and late Delta, we had these enormous waves of Delta in the secondary schools and Omicron in the primary schools, and so of course that was going to be reflected in this analysis. So thanks to everyone. That was it.
Great, thanks, Thomas. I don't